Mr. John, would the second lens have like a downward set of various frequencies?
Well, we will see. So, polarization. Um, so what we noticed is that if we take a polarizing filter, right, and we place it on a lit surface, in this case a projector, when we just put one polarizing lens on there, there is a decrease in the amount of light getting through. It just looks like, you know, a cheap sunglasses lens or something from the store, okay? But when we put another polarizing lens over top and we turn it, we notice that we go from a light to a dark. In other words, light gets blocked out. And as we rotate it full circle, it pops up to being light again and then dark again and light again and dark again. So we want to know what the heck's going on. Okay, so here's a couple pictures. These are both polarizing lenses. Okay, we're laying them on the surface of the projector here, so light's shining through. You can definitely see that there's some dimming within the lens area as compared to the surface overall. I've got a protractor attached to this lens, and I have a pin attached to the other lens. You can see it there. The first thing I do is I lay the lenses over top of each other, and you probably don't notice a whole heck of a lot of difference between a single polarizing lens and the two lenses laying on top of each other oriented in this way. You'll also notice some weird artifacts here in terms of the plastic. We'll maybe mention that in a little bit because that's kind of interesting as well. So now what I'm doing is I'm leaving that bottom polarizer to sit still, and I'm turning this one, and you can see the arrow here has moved over, so maybe around 30 degrees or so there. And here we would say we're at, say, 0 degrees. And over here, we'll call that 90 degrees, okay? And what happens is, when I crank that over to 90, okay, I think I went just slightly past, but when I crank it over to 90, you'll notice that there's a very clear difference in the amount of light that goes through. It's almost pitch black. Basically, no light is able to leak through here. Now, you might notice that you could see the protractor, which is sort of weird, right? Because the protractor is glued or taped, I should say, onto this bottom lens. Okay, and when I put the second polarizer on, anywhere that it's just lens over lens, it's dark. But where the plastic is between the two things, something weird's happening. Light is actually able to get through there. So we'll talk about the basic theory as to why you go from first just dimming, then as I crank the polarizers with reference to each other, you go to darkness, and then at the end we'll mention what the heck's going on with this weird plastic causing the light to be able to go through. Okay? All right. So a polarizing lens is able to filter out some of the light incident on it. Okay? Leaving, and this will make sense in a minute, but leaving polarized light to shine through, let's say. All right, so what that means is, in this case up here, right, this is just normal light shining through. Here, though, through the polarizing filter, what's coming to our eyes or to the camera, this light is polarized. Okay, so the light coming through the filters to our eyes is polarized. So what does that mean? Okay, so I'm going to see if I can draw something for you. And we'll imagine a situation where we have a light. Let's make it an incandescent bulb. Okay. And we'll draw a wave ray. Okay, so this is just going to, basically show us the direction that a beam of light is traveling out of this light bulb. All right. Now the light coming from the bulb is not polarized. So what that means is if you want to think about light as a transverse wave, okay, it shows some wave-like properties. So, I mean, we're going to talk about light as a wave, whether it's really a wave or what its exact nature is a little bit beyond the scope of what we're going to talk about today. So we're not going to talk about like the quantum mechanical version of light. We're going to talk about light as it's understood in the wave theory version of it, okay? So the way we look at it is a transverse wave traveling, but the transverse wave is not oriented in any particular plane. So what happens, or the way we imagine this, is that light is coming out of here in such a way that its crests and troughs can be at any possible angle we can think of. Here, maybe I can draw that a little bit better. Hang on a sec. I think I have some tools to make that picture a little nicer. Yeah, I know. It's like kind of like cheating for me. I get it. Okay, so the easiest one to draw, right, is a full amplitude, as if light were, you know, a one-dimensional wave. So we could imagine that we'd have okay. So that's like oriented, let's say, in the so we could say this is maybe the x-axis, this is the y-axis, and this is the z-axis, sort of coming out of the paper towards us, okay? And we've drawn this oriented so that it's vertical or in line with the y-axis, but traveling along the x-axis, okay? So there's no part of this wave in what I've drawn here that's into the z-axis, all right? It's perfectly vertical in line with the y-axis, traveling this way. That's what I'm trying to show. Now, there's nothing to say, though, that I couldn't take this light wave and tilt it to the side, all right? So if I were to tilt it to the side, and I imagine on this axis, well then some of the amplitude would go back into the page. We will draw that as dots, and come out towards us into the z-axis, okay? So we're going to have to imagine that some of this light is oriented sort of into and out of the page. So I'll see if I can draw that. Not sure if that's going to look right, but some of it is rotated off axis a little bit. And really, there's an infinite number of possibilities for the way that light could be oriented with respect to that y-axis, right? It could be directly in line with it. It could be at 90 degrees to it. It could be at 30 or whatever. It could be in any kind of orientation. And we just imagine that it's somewhere in this circular tube. So we could also have some that's like oriented back and forth the other way, like so. Okay, so it could be rotated in any angle. Does that make sense? Okay, so now what we'll do, okay, so this is light oriented at any possible angle. So if I imagine that I'm looking at this direction, okay, so here's my eyes seeing this, what I would see is I would see this. I'd see a circle, right? I'm looking down this like tube of light, if you want to imagine it like that. And I am seeing amplitudes of light at every possible conceivable angle that exists. I'm not going to draw this very well. It's going to be annoying. See if I can fix it. I think the problem is I should have put a dot in the middle. I don't think my middle is actually the middle. Let's try that again. The middle's got to be the middle. There we go. Okay. All right. Try that again. Nice. So this just represents those beams of transverse light coming towards your eye at all possible existing angles. All right, so that's what you'd see. All right, I'm just going to draw a few of them just so you get the gist of it, right? And you know, the first one that I drew would be like that vertical one right there. Okay, so that might be the first one that I drew. That was very clear and easy to draw. The rest are just oriented at various different angles with respect to the y-axis. So far, so good. Do you get that? All right, so now I'm going to plop in front of there a polarizer. Okay? So a polarizer is going to do this. Okay? I got my light coming in. So let's just redraw that. Okay? My waves are oriented at like any angle. So maybe like this, like that, like that. Okay, so as they move along, they're oriented in any possible direction. Now what a polarizer is going to do is it's going to behave almost like a picket fence. Okay, so we're going to imagine that we're going to pop right in front of this thing a polarizing filter. Okay, so there it is right there. Actually, I don't really like the way that looks. I'm going to fix that. It's going to look like this. Okay. I should actually probably draw it a little farther back even than that. So it looks like it's actually going behind the light. There we go. That's better. Okay, so there's a polarizer. Now, what you have to imagine is that this polarizer is made up of a bunch of strands or slots. Okay, so we're going to draw these just as vertical lines. We're going to say this polarizes in the vertical plane. So what are these in reality? Well, they're basically certain chemicals that interact with light. And what they do, essentially, is they block out the fraction of light that is not in the y-axis. All right? So what ends up coming out the other end, then, is this. Oops, is this. I always do that.
The unmatched power of the sun. So, polarizers are kind of like bouncers that would only let certain rays of light through, therefore decreasing the amount of light that gets through in total.
Yeah, right.
That makes sense.
So all that comes through then is the light that's in the same orientation as the strands of chemicals in the polarizer.
Okay, and I'd just like to, I want to jump on the gun here, but then when you put those two polarizers together and you adjust the angle, that is decreasing the slots that like light can go through. So if you adjust it so much that there's only like a tiny.
Okay, so some people are noticing that if I took another polarizer and I put it over here and I turned it 90 degrees so that now my polarizing slots are vertical, kind of like this. That's not what that's supposed to look like, but if I turn them so they're vertical, okay, they're going to cut off, or horizontal I should say, they're going to cut off the amplitudes from these vertical waves, and you're going to expect that you'll have no light being able to pass out the other end.
Does sunlight actually get out of there, or does it all get canceled out?
Well, I mean, I think it comes down to one of those theory things, right? Like, if these things were perfectly made, theoretically, you would have zero light getting through the other end, right? If you orient them exactly at 90 degrees, right? The polarizer and then the filter, I believe is how you call these things, or a filter and a polarizer. A polarizer and an analyzer. That's what they call this thing. So the second polarizing filter is called an analyzer. As you turn the analyzer with reference to the polarizer, you either let through all of this secondary light, or as you turn it, it drops down to no secondary light coming through there, okay? So that would block all the light. So two polarizers should theoretically be able to block all light traveling through them, okay? Now, of course, as always, there's going to be some math, okay? Okay, so the first thing to note is this. Last time we talked about intensity, right? What was the intensity of light? Do you remember?
Isn't it intensity is proportional to 1 over radius squared?
True, but what's the definition of it? Right. So it's units then, power being watts, which is joules per second, right? Spread over some area. So units then, watts per square meter, right? Watts per square meter. The intensity here we would consider to be full intensity. Now the first polarizer drops the intensity here to 50% of I. Okay? 50%. Which you might think is weird. Does anyone think that's weird? How do you get 50%? All right, so why 50%? So the way that I look at it or think about it, and it's probably not perfectly correct, but it's probably as good as we're going to get at this stage, okay? If we imagine that, this is, the y-axis and this is the x-axis, we could say that 100% of Y light gets through. And 0% of X-oriented light gets through. Okay? So unlike a picket fence, it's not quite a perfect analogy, some fraction of the light does get through depending on what angle that light strikes the surface. When we say what angle, we're talking about what angle to the vertical in this case, right? So we'd say that that light is 0 to the vertical, that's maybe 45, and this is maybe at 90, okay? 0% of that gets through, 100% of this gets through, some fraction gets through here. It's actually going to be a trig function that gets through there, right? So we'll look at that in just a second. But if we take 100% for Y, 0% for X, and we do a simple average, you get an expectation that about 50% of the total intensity striking the polarizer is going to actually make it through. Okay? Now someone might say, where does the rest of it go? And I would say, I'm not sure. Heat, maybe? I don't really know. Okay, so just to be clear here now, we do have some transmittance of light that's off angle, right? So to try to show you what I mean by that, let's imagine you have this, okay, and let's imagine you put a polarizer in front of it, and the polarizer is a vertical polarizer, okay? It's a vertical polarizer. So we're looking end on at the light, right? Just like here. So, if you were to imagine that you have, your kind of unit circle that we're talking about here. Now, if light is perfectly vertically oriented, we get 100% coming through here, right? So that's not too hard to understand. That makes sense. 100% of any vertically oriented light makes it through our polarizing lens here and comes to your eye, okay? And 0% of any horizontally oriented light comes through. But what about light that's oriented here, like this? What fraction makes it through here? So remember, this is representing the amplitude of the light, okay? And what's allowed to come through here now is only the stuff that's in the vertical plane, right? So we've got a vertical polarizer. So it would be this fraction here and this fraction here that would make it through, okay? So, you know, if I change it to a different angle, we're going to end up with a different amount of light coming through there, right? So by the time I get close to horizontal, the amount of light actually like making it through becomes smaller and smaller and smaller. So maybe another way to look at it, maybe it's just something you want to just remember. I'm not really sure, but that's the kind of way that I talk about it to myself. Now, the net effect of this, okay, is that you're essentially chopping off any part of the amplitude that's not in the vertical plane, and you're getting out the other end only vertically oriented light. So let's draw the picture again, and then let's talk about what happens when that polarized light meets an analyzer, okay? So one more time, light bulb. Okay, we'll draw ourselves a little arrow here. Okay, we'll draw a polarizing lens. So put our vertical slashes in there. Doesn't have to be vertical, it's just probably easiest to be vertical. Okay. Into the top end here, into here, we get, you know, 100% intensity, right? Watts per meter squared striking the surface. But this is unpolarized light. It's coming in at all possible angles, right? It's all jumbled up. Then, whichever light strikes perfectly vertical, that gets through. Whatever strikes horizontal gets blocked out, and we get some fraction of light at other angles making it through. But all the light coming out the other end is now vertically polarized. And it's dropped to 50% of the incident intensity. Okay? So this is what comes out of here.
So since that's a vertical light, per se.
All right. So what we noticed then is that if we placed our analyzer, you know, in line with this thing. Remember, our analyzer is just the second one, right? Polarizer is the first one, analyzer is the second one. And if we vertically orient it, what we will find is that 100% of the incident polarized light comes through the other end. Okay? So remember, there's 100%. This is now 50% of this, okay? But of this 50% that comes to here, all of it goes through, right? Exactly. All of it will go through. Nothing's cut off. Okay? We're going to get to math here in just a second. We're good. But what we're going to now do is we're going to start to rotate this thing, and we're going to rotate it 90 degrees. And in the process, this light's going to get dimmer until we get 0% of that light making it through. At 90 degrees, you get 0%. So we're interested then in what happens to the intensity at various angles between these two things. Okay? So let's just look at the area that we're interested in. Okay? What's going on with this polarized light? Okay. So we'll draw it like this to make it easy. Draw a line. And we'll just draw some vertical slashes on it, just to indicate that we have incident polarized light striking onto our analyzer. We want to know what happens if we put it at some random angle. You know, like maybe like this. Okay, so what's going to happen? Well, some of the light's going to make it through, but how can we figure out how much? So what we'll do is this. We will say this. We'll imagine. Okay, so let's imagine this. Here's my analyzer, okay? And we'll say that it's a vertical oriented polarization lens. Okay, so remember, just an analyzer is the same thing as a polarizing lens. It just comes after the polarizing lens. So again, it's rolling up here. This is the polarizer. And this is the analyzer. Okay? So now what we want to do is we want to say, okay, this is going to represent the incident light with respect to the polarizer, okay? Or the polarization direction. So what fraction of this light's going to get through? So if I look here, I would say that this is A naught. In other words, this is the amplitude of the light striking the surface, okay? And what we want to know is we want to know what fraction is actually going to make it through here. So we'll draw a line back into here, and we'll say the fraction of this, total amplitude that's going to be able to pass through this thing and continue on, it's going to be designated by this, right here. What color should we make? We'll make it red. Okay, so that red line I've just drawn, this is the portion of the original amplitude able to pass the polarizer. All right? So if we imagine then that we have an angle, theta, and we'll say if you are directly in line with this thing, okay, you've got an angle of 0, and if you're at 90 degrees, okay, you have an angle of 90 degrees, or if you're horizontal to it, you have an angle of 90 degrees. This way. So, what's the amplitude of the portion of light going through there? So the way you would write that down is you take the full amplitude, and you'd say, let's call it A. A that's coming through is the amplitude on the other side of the analyzer. Is going to be equal to A naught times the cosine of theta, right? It's the adjacent angle. A naught is the hypotenuse, so A naught cos theta is the amplitude that's actually able to pass through the analyzer, okay? So what's going to happen here for this particular angle of light, whatever it happens to be, the amplitude making it through the analyzer is going to be some smaller fraction. So let's see if we can draw it from the side here. All right, so we got this. Okay, we've got light at some angle, whatever it is, to the polarizer, or to the analyzer, I should say. So here's the analyzer. Draw it real quick. Okay, it's vertically oriented. Here's our incident light. It's coming at some angle. Say it's like 30 degrees. So what ends up happening is the light that makes it through here, okay, is going to be polarized, but the amplitude is going to be knocked down significantly. Okay, so we get a new polarized wave that's oriented in the same direction as this one is, but with its amplitude chopped down. If I were to come in at 90 degrees, you can see by the time I get to 90, A naught, whatever A naught is, times the cos of 90, well, cos of 90 is 0. So 0 amplitude comes through, right, the other end. Now, we're almost there to where we want to get, which is Malus's law. So what ends up happening here is we have to remember from last class that intensity of light is proportional to the square of the amplitude, okay? So we learned that in terms of like the kinetic energy of oscillating masses, and we learned that if you double the amplitude, because the kinetic energy is related to the speed by a square, then the amount of energy carried at twice the amplitude is actually 4 times higher. Or if it's, the amplitude's 3 times, you're going to have 3 times the velocity of that mass coming back across the center, and you're going to get 9 times the energy carried. So since intensity has power in it, and power is related to energy, we worked out that the intensity of a wave is proportional to the square of its amplitude. So what we want to know then, okay, is if we imagine this as the incident intensity of polarized light, what happens to that intensity as we strike at various angles to our to our polarizer? What happens at various angles? We know at 90 none can get through, and we know at 0 degrees all of it gets through. But what about at like 30 degrees or 50 degrees or whatever? So what we could say, and what we've sorted to start out is we've sorted this out. So then, if that's true, and this is true, right? And our new light intensity is related to this amplitude that's after that polarizer. We could probably do a proportionality that takes that into consideration. So we could say then the intensity of light on the far side is probably going to be proportional to that. Okay? Or in other words, the intensity of any light is proportional to A naught, is proportional to A squared. The intensity on the other side of this is proportional to A naught cos theta squared. Just to remind you, okay, we're talking about amplitude here. I can see why you might get confused, because intensity is power over area, okay? And its units, of course, are watts per meter squared. Amplitude would just be in meters, right? How tall the wave is, okay? Okay, so now, let's take this thing. We say, okay, I, intensity, is proportional. Okay, we're going to square this whole thing. So we can square the first part, and we can square the second part. Now remember, when you're squaring this whole thing, it's written as cos squared theta, not cos theta squared. That's something different. Okay? Okay, you're not just squaring theta, you're squaring this whole thing, right? So you get that. Okay, we're almost done. We may not know this. Okay, but we do know this. Right? Intensity naught is proportional to A naught squared. Right? That's from last class. We learned about that. So we may not know what the actual amplitude is, but we know that the intensity will always be proportionate to the square of that. So what we can actually do here is we can do a substitution. We can say that where we see A naught squared, we can substitute in an intensity naught. And then we can have an equivalency. Like so. All right? Now the name of this thing, and if you're unsure why, I mean, that just goes back to this concept right here. Whatever my intensity is proportional to the square of the amplitude. All right? This has a name. This is Malus's law. And this is exactly what we're observing when we take a polarizer and we rotate an analyzer over top of it. So, for practice, oh yeah, sorry. It's Malus's law. Okay, calculate the intensity if, actually, sorry, let's do it this way. Do a little more IB-ish. All right, so what fraction of the I naught remains if polarizers are stacked at a 45-degree angle to each other? All right, so we'll imagine then that I naught, let's call it 1. And that could be watts per meter squared. Okay, and we want to know what fraction of that makes it through. So really, it's quite simple. We're just going to go I naught is equal to 1 cos squared times 45 degrees. And we'll see what we get. All right, so this basically just evaluates to this. 1 times cos 45 degrees and square the whole thing. So what you get is 1 times 0.5 or 5, which is 50%.